Testing, testing. Oh, great. All right. Welcome. Hello, everyone. Welcome to another CSE for Certain lecture. Today, it's going to be a guest lecture, and the guests are your TAs. I'm Stanley, and this is Nahush. Hello. And our topic today, our topic today will be two parts. The first part is a comparison between functional programming versus object-oriented programming, and the second one is the comparison between static and dynamic typing. Yeah, and let's give an introduction to our guest lecture. So first, I'm Stanley. This is my junior year at UW. I major in computer science and math. I've TA'd this class for 6 times, so yeah, I'm fortunate to be here again.
Hello everyone, my name is Nahush. I'm also a senior studying computer science. I'm actually graduating this quarter, so I'm super excited but super nervous at the same time. I've been taking this class for 3 quarters now, and it's been pretty amazing. So just some administrative details before we jump in. Your final is on Monday of finals week, which is June 9th. It's in the same room from 2:30 to 4:20 p.m. Your last lecture will be on Friday of this week, and that will be a final review during lecture time. We highly recommend you guys to attend because a lot of the questions that we'll be going over will be similar in format to what you'll see on the final, so it's always great to be prepared. Homework 7 is due tomorrow, June 5th. You can still use all of your 4 late days if you want to, so no late submissions after Monday, June 9th, 11:59 p.m. Finally, we don't have any office hours next week. You guys can still post questions on Ed, and we'll be happy to answer them. But yeah, just keep that in mind. Let's keep this in my hand. Okay. Any questions about administrative details? Nope. Cool. So let's get started. So the first part of the lecture is going to talk about object-oriented programming versus functional programming. But before we jump in, let's just first define what these two things are. So functional programming is basically a paradigm where we decompose our programs into functions that perform some kind of operation. You can kind of think of functional programming where functions are king, and you guys might have been hearing this throughout the quarter where functions are first-class citizens. Functional programming allows you to do a lot of crazy stuff. I mean, things like currying, high-order functions, they came from Lisp, which is kind of functional programming. So functional programming is a very powerful paradigm, but a lot of people don't use it just because, I don't know, I guess it's intuitive for them, or they've never been introduced to it for the first time, and I guess object-oriented programming got more popular, which we segue into object-oriented programming. So it's a paradigm where we decompose our programs into classes that give behavior to some kind of data, right? As you guys know, classes is just some kind of object that is built up on top of some other type of data type. That can be a primitive type, that could be another class, it doesn't matter, right? And that's sort of the beauty of object-oriented programming, right? Because you can build a lot of crazy stuff from there. I mean, all the data structures that you guys may use in, say, 123, 122, things like hash map, hash set, all of that stuff, those are just classes that we built in object-oriented programming. So these are two very powerful different paradigms. And the key insight is that they're exactly the opposite, but they're not very different altogether, right? It's kind of unintuitive, but you can kind of think of it like they're two sides of the same coin, right? At the end of the day, whatever program you write has some kind of functionality, and it's written to perform some kind of task, right? So they're not really different in that sense. It's just the way that you're solving that task, or the way you're solving the problem. That's the only thing that's different. And that difference causes how that difference is determined by what your use case is, what your personal taste is. It's really subjective, and there's no right and wrong answer here, right? So functional programming and object-oriented programming, they kind of fill out the same matrix in different ways, which is the same thing as saying that they solve the same problem. They're just in two different directions you can kind of think of. there's no really right and wrong answer. It's just a matter of personal taste. And it's kind of like writing in cursive versus writing in block letters, honestly. We're going to use a matrix example in the next slide. It really helps you understand and visualize this difference and how functional programming versus object-oriented programming, which one is better for what. So let's jump into that. This is a very common way to visualize the difference between the two paradigms. This is a famous expression problem. I'm sure you guys are familiar with expressions from homework 6, right? So we have different expression variants. You can kind of just think of them as data types. You have int, add, negate. And we put our data types from the rows. So this is where we populated them. And then we have our operations or the functions that we want to define for each of these data types as our columns. So we have eval, toString, has0, right? And this is just a simple example. You guys can expand this. I mean, it could be a 10 cross 10 matrix. It doesn't matter. This is a simple example. And obviously, as a programmer, you want to define all the different, you want to kind of fill out this whole matrix, right? You know, for all of these different data types, you want to define all of these functions and vice versa, right? So this is how we're going to now view like this whole debate. We're going to view this through the lens of this matrix. Any questions? Cool. So first, let's look at some code. But before that, the functional programming approach is by column, right? And you guys could have guessed that because, I mean, we have our functions in the columns. And what we do in functional programming is that we kind of fill this matrix column by column. So our approach in functional programming would be to solve for this eval function over here and then write different cases for that eval function. What case would come for int, what case would come for add, what case comes for negate, right? And that's kind of the basic structure that we have in, say, pattern matching, for example, right? You guys literally just do match E with, int, add, negate, right? It's literally the same pattern. And so what that actually looks like in code is, so if I just jump into this OCaml code. Yeah, so here we have our type expression where we've defined our different data types. This is the helper function to add stuff. And here, so over here you guys can see that we start with eval and we are having different pattern matching cases such as int, negate, add. The same thing is there with toString, int, negate, add, and then same thing with has0. So you guys can see this is like the general pattern for functional programming. It's literally just column by column, eval, toString, has0, fill each row. So match E with int, negate, add, right? Pretty straightforward. This is what we've been doing throughout the quarter. And it worked. It's perfect. I mean, you guys literally wrote an interpreter in Racket for this, so pretty cool. Object-oriented programming, on the other hand, is by row, right? And hold up, let me just go into slideshow. Actually, never mind. Anyways, object-oriented programming is by row, and what that means is it's just the opposite of what we just did for functional programming. Instead of filling it by column, now you're going to fill it row by row. And so for each data type, you're going to write 3 different functions, eval, toString, has0, right? And the roles are kind of flipped over here, so the data type is sort of king. You can kind of think of it like that. How does that look like in code? We look at some Java code over here. So you can see that we define a class, and we declare that it has to have these 3 functions. This is just some object-oriented programming jargon. And then over here, the main stuff, over here, we first define our class int, right, our data type int, and we define the different functions that we'll have. Get I is the same thing as eval, right, because int will evaluate to int. And then, yeah, you have your toString and you have a has0. And the same thing with negate and add, right? So it's literally the same thing, just flipped over. Cool. So one thing you guys might have noticed over here is that in Racket over here, we have examples where you have functional programming and you have object-oriented programming. But I picked these two examples where they're in different languages, and that's there for a reason, right? A language is, when someone designs a language, they kind of design it with some sort of problem that they're trying to solve, right? Java, for example, Scala is a language, is a functional programming language that was written to solve the problems in Java, right? Similarly, Java is a programming language that is really suitable for object-oriented programming, and it has a lot of cool stuff like inheritance, polymorphism, all that kind of stuff. And on the other hand, OCaml is this great language which has pattern matching. It has a lot of strict type checking. The type checking is what actually helps you, kind of find all the different rows that you have to fill. You can kind of think of it like that. And that's the reason why it kind of throws an error when you don't match a certain case, because then you haven't actually filled your matrix, right? So this is just, I wanted to illustrate that different languages are there for different purposes. And again, there's no right and wrong answer on how you solve a problem. Based on your use case, if you have to use, for example, if you have to use C++, then you're probably forced to do object-oriented programming and not functional, right? Because that language has been made for object-oriented. So again, no right and wrong answers in this. It really just depends on your use case. And again, just reiterating what I just said, it's doing the same thing in just exact opposite ways. It's really just a matter of personal taste and what you prefer, honestly. I can give you guys an example. So I'm part of this engineering club on campus called Washington Tunneling. And I was tasked to write this code base, microcontroller code for this machine, and it's interacting with a lot of sensors, right? Because it's microcontroller code, that means I have to write this in C++. And I didn't really have a choice to write it in functional programming at that point. So I had to write it in object-oriented programming way. And when I was writing this out, I didn't really even think about what paradigm I'm going to use. I just went with the flow, kind of, right? And that should kind of give you like an idea that when you start out a new project or when you start writing out a new program or software, don't really think about, hey, I'm going to do it this way or I'm going to do it that way. You're trying to just solve the problem, or you're trying to fill out this matrix. It doesn't really matter how you do it. The great thing about taking this class is that most of you would probably already know object-oriented programming, but not functional programming. And now you know both of them, and you can kind of employ techniques from both of them, right? You can use classes and you can use higher-order functions at the same time. It works, and it gets the job done, and that's what matters. Other than that, your choice really just depends on the application domain and team aesthetics and all that stuff. There's a lot of tools that can help you write this kind of code. Like, there's a lot of tools that can help you write object-oriented programming code because it's such a common thing in industry. You guys can keep that in mind as well. Anyways, why do we care so much about this debate? A big part of it is extensibility. And so extensibility is basically how we design our programs for the future and how we extend our programs to include more functionality, right? In other words, it's basically us just growing out this matrix, right? Because things change, you want to add new features, all that kind of stuff. And so you want to think as a programmer, how well are you going to plan this out, and how easy you're going to make it for yourself, or how difficult are you going to make it for yourself. In this debate, we have two different things. If you need to add a new kind of expression variant or a new data type, basically if you need to add a new row, then it's annoying in functional programming, but it's very easy in object-oriented programming. And the vice versa is true in the other case where you need to add a new operation. It's annoying in object-oriented, but it's easy in functional. Why is that? Let's kind of see that in an example in code. So if I just go to version 1.ml, one sec. So if I go to version 1.ml, the functional programming code, and I want to add a new data type, what would I have to do over here? I would basically just add a new branch condition over here, right, for match. But the thing is that I have to do that for every different function. So I have to do that for eval, toString has 0. And obviously over here it's just adding 3 lines of code, but you can imagine a code base with like 1,000 lines of code and like hundreds of functions, and that's very annoying. And one thing to keep in mind is that, once you submit some code to production, it's already tested, it's already validated, right? You've kind of ironed out all the bugs. But once you change a function that's already been validated, that means you'll have to test it again, because there's no guarantee that that code is correct and bug-free. So that's another hassle that you have to worry about, and that's why it's so easy to add. That's why it's so difficult to add a new data type in functional programming. On the other hand, in Java, it's pretty easy, right? How I would add a new data type, like say subtract, I would just make a new class and I would just write new functions for it. The great thing is that I'm not editing any of the old data types and any of their function definitions, right? I'm not adding anything over here, so this thing which has already been tested I don't need to test it again, and I don't have to touch it, which is a great thing. It's less work. We all love less work. So yeah, that kind of is a very simple example of why it's easier in object-oriented. And okay, well, I guess I had the wrong slide on, but on the other hand, with functional programming, it's easier to add a new operation, right? So if we go back to our example in OCaml, me adding a new function is just the same way I added a new class in object-oriented, kind of. So I'm literally just writing a new function block. I'm not editing any of this, and I don't have to test all of this again. So much easier. But with Java, it's kind of a pain in the butt. So I have to go inside the class. I have to kind of write new functions for this, and I have to kind of test the class again. So same problem that we saw previously. So this is just like a very simple, demonstration of why it's difficult to add a new operation in object-oriented. And so what's the point of all of this, right? In reality, we don't really know what we're going to be doing, right? I don't really know if I will need a new data type or I would need a new function. So extensibility has its downsides. You can't really plan for the future. If you could predict the future, none of us would be here. And it gets harder to understand and it gets harder to maintain as time goes on. What you can do is you can kind of restrict the edits that you have to make. So for example, you can use the final keyword in Java, which kind of just says that, hey, this thing is locked and you cannot edit it, and we do not want to mess with it. And that's really important for, like, say, utility functions, which a lot of different programs depend on, right? Your biggest job as a programmer is to worry about correctness. So when you're doing extensibility, you tend to mess things up which were already correct, and that's not good, right? So how can we try to solve this problem? If you know new operations are coming, you tend to use functional programming, and then if you know new data types are coming, you tend to use object-oriented programming, but it's not that simple. Again, it's a mix. So you can use languages that try to support both, but there are trade-offs in these approaches. For example, there's Scala, which is, again, I mentioned, it's a highly, I think it's very strict typed functional programming language that was made to improve upon whatever Java has. I highly recommend you guys check it out. I feel like the learning curve is not going to be that difficult because I'm assuming a lot of you guys know Java. And there's other different things that you can do. For example, in object-oriented programming, you can plan ahead with advanced techniques like visitor pattern. And there's a lot of different things we learn in this class. When you're choosing language, you have to worry about things like, for example, mix-ins, inheritance, passing by reference, passing by value. There's a lot of different things. So yeah, that's why we have a whole different field called programming languages. But yeah, that's it for this part of the lecture. Do you guys have any questions? All right, cool. I'm going to hand it over to Stanley, and then he'll cover the static versus dynamic typing.
Let's give a great And applause to our speaker, Nahush. Thank you. Yeah, that was great. The next topic that we're going to talk about today is static versus dynamic typing. Again, we give credits to Professor Dan Grossman for his wonderful slides 2 years ago. Yeah, all the slides are based on his slide. So first, let's take a look at OCaml versus Racket. That's the two languages that we mainly learn today, in this class. So they have a lot in common. They'll have closures, first-class functions, mutation only as needed, and let expressions. By the way, a small note about mutation. So in OCaml, one common thing that people write is let x equal to 3, and then people might write let x equal to 5. So is this actually mutating the value of x? This is not actually mutating x. What actually happening is that people are relabeling the value of x from 3 to 5. So this is kind of like creating a new x that just like totally erases the old x. So no mutation is happening. So both OCaml and Racket, they don't really do much of mutation. But there are lots of key differences between the two languages. They have different syntax, they have different scoping rules and semantics of let. One have pattern matching and the other has lots of struct features. But the biggest difference between these two is that OCaml is statically typed and Racket is dynamically typed. Let's do a quick poll. So please raise your hand if you would prefer writing OCaml code over Racket code. We have a lot. What about, would you prefer Racket code over OCaml code? Looks like people love OCaml a lot. Give me a sec. All right. So let's jump into the topic of typing, of like the difference between static and dynamic typing. Not sure if we can capture my voice. So we have a few key questions that we try to go over. First, what exactly is type checking? What is static and dynamic typing? And second, why is static typing checking? We call this necessarily approximate. So static type checking is just an approximate of the actual type checking rule. And the third one is the pros and cons of using static checking. But before we jump into that, let's first try to gain a useful perspective by imagining how would a Racket programmer describe OCaml and how would an OCaml programmer describe Racket. So imagine in a universe we have two different planets, the OCaml planet and the Racket planet. There are no communication between the two planets. So the programmers from one planet will have no idea what the programming on the other planet will be. So let's imagine a Racket programmer who spent their entire life on the Racket planet just suddenly gets teleported to the OCaml planet. What will they say of like all the OCaml language? Let's assume that all the OCaml language that we are talking about here, they are safe to run. Like at least you can run them. So if we ignore all the syntax, OCaml is really just a very well-behaved subset of Racket. So in Racket, people can write like all kind of arbitrary things, such as like counting a number to a string to produce a pair. Actually, that's not a good example. Like in Racket, people can write like lists of like arbitrary types. For example, the first of the list could be an integer, and then the next one could be a string, and so on. But this is not allowed in OCaml. So OCaml is really like a very well-behaved subset of it. So for example, you cannot pass a list to a plus or a number to a car. So in this subset, there's no need to use type predicates like number ? Because if an OCaml code can run, it guarantees that all the types, all the errors related to type, they are already handled. So at the compile time, an OCaml language already knows that if this code is runnable or not for every expression. But there are also many useful programs that are not in the OCaml subset that could also make sense. For example, a list of alternating strings and numbers or returning different types from different branches. OCaml just doesn't allow that. So yeah, a little sad. But what about a OCaml person just suddenly get teleported to the Racket planet? So one view that we can have is that Racket is just it just uses a very, very big variant. So all values, all the possible values that you can imagine from Racket, whether it's a integer or a pair, a function, or a Boolean, etc., anything that you can imagine, they're all built from this variant called the type. And what constructors are actually doing there, they're just like applied implicitly. So like imagine in the Racket code you read 42. The OCaml person can just think of this as like it is tagging the constructor integer to this 42, as this int tag is doing. What's the point of doing this? The point is that is that for our camel code to run, it need to make sure that all the values in this program, they are kind of closed under this type. So let's take a few examples here. So the car case. So the car function, we're taking a v. This v can be any value of the type. So it would do a pattern matching on v. If v is a pair, then it will take the first value of pair. Otherwise, it would just fail. For the pair question mark thing, what it does is that it will tag the constructor bool to a match statement. If v is a pair, then it returns true. Otherwise, it returns false. So yeah. Any questions so far? Cool. So now is the time to talk about static checking. So static checking is anything done to possibly reject a program after it successfully parses but before it runs. We'll take a look at some examples later. This might be a little bit abstract, but like one very small example would be static checking will reject any program that tries to add a integer to a string or something like that. A common way to describe a programming language's static checking is called a type system. The purpose of a type system is to try to prevent all the errors that violates all the type safeties. This will definitely enforce modularity. Yeah. The benefit of doing this is that anything made impossible due to the type system, there's no need to check them at the runtime or dynamically, because the program just rejects all the possible ways to do that. So yeah, that's what static typing do. They use a type system to prevent various errors. But the dynamic typing, on the other hand, they are on the opposite. They do little or no static checking. And the line between the two could be fuzzy, but usually clear. Just like notice that we say that Racket is dynamic type, but it does some basic checks, such as it detects all the undefined variables. On the other hand, OCaml, it is statically checked, but it do allows this kind of statement. It do allows us to like try to get ahead of a list, of an empty list. This works under type safety because a list is a list, and the list of head would expect that the first argument or the argument passed into list of head is a list, even though in runtime this will fail. So yeah, time to look at some examples of what OCaml type would prevent. It guarantees that a well-typed program will run. It will never use a primitive operator on a value of run type. We've seen that. It will never try to access a variable that doesn't exist. It will never evaluate a match with no matching pattern. You guys can recall when using match, there's always this warning saying match not exhaustive. That's the check there. It also guarantees that you will not violate the internal invariance of a module. In general, different languages type system that would prevent different things. Yeah, but there's something in common, which on the other hand, what do the type system actually allow? So there's plenty of other errors that are still possible. It would allow functions that would raise an exception, such as list ahead on the empty list. It would not catch array out of bound errors. It would allow division by 0, etc. One thing to notice is that there are fancier features, fancier type system that actually can catch all of them, but they're harder to use. Yeah. Without a full specification, no type system can catch all bugs. We're going to take a look at that later in this talk. But just imagine that if a type system, if like you want a type system to try to catch to catch something that's wrong, you have to reverse all the branches of a imagine you just reverse the branches of a conditional. Does the type system know that you actually do that? It does not. So yeah, so a type system is only going to catch everything related to type, not on the logic side. Any questions so far? Cool. Yeah. So let's take a look at what the actual typing rules are. So there's a question of eagerness. The eagerness is like, what time would a programmer prefer to catch the bug? How many of you would prefer catching a bug before it matters over just do not care about a bug, do not report it until it actually matters? Could we do a quick poll? All right. How about we just don't care about a bug before it actually matters? Nice. So yeah, so static checking and dynamic checking, they're just 2 points on this continuum. So let's take a look at this silly example. So we all know that you cannot divide by 0. So there are 5 different time frames that this checking can actually happen. It can stop the programmer from doing that in the keystroke time. It just directly yells at you when you type 3 divided by 0 in the editor. It can also happen at a compile time. When the code is trying to compile, whenever it sees 3 divided by 0, even though this is never run, the compiler will stop you from doing that. It can also happen from the link time, which means so link time is just it's a stage in the compiler that pulls all the dependencies for the code that you're running, and it is about to produce an executable. So it can stop you from doing this whenever you see that the main function, the function that everyone is going to run, uses 3 divided by 0. You could also go to the runtime, which is very similar to what Racket does, is that it only yells at you when you actually run that code. And what's even more interesting is that it can just never report any error. It can treat this 3 divided by 0 as a special value, such as positive infinity. This is how C or C++ does. So yeah, this is a very interesting question. So it's about correctness. So yeah, let's talk about how type system works with correctness. So the purpose of a type system is to prevent some X, which are some bad behaviors. So a type system is called sound if it never accepts a program that, when run with some input, it does X. This is also called as no false negatives. A type system is complete if it never rejects a program that, no matter what input it is run with, it would not do X. So a complete type system, it would never reject programs that are good, basically. And a sound type system, it would never accept any program that would do something bad. So one very silly example of a sound type system is that it just rejects all program. No matter what we give you, it will reject that. This type system is clearly sound because whenever input you gave them, it will never do X. So yeah. So the goal of the usual goal for a programming language type system is try to be sound, but is not complete. We'll also take a look at that in later slides. But all the fancier features that we mentioned previously, just like generics in Java, they all aims at getting fewer false positives. So Venn diagrams. This is a very great way for us to visualize. So imagine this, this blue rectangle is the space for all possible programs. There are two mutually exclusive parts. The left side is the programs that are bad, there exists at least one input that will make the program do bad thing X. And the right side is all the programs that are good. There's no input that will make the program do bad things X. So a type system that will accept all the program in this yellow circle is called sound but incomplete. It is sound because every all the program outside of this circle will be rejected, which includes all the programs that are bad. That is why it is called sound. Yeah, it is incomplete because it actually rejects some programs that are good. So all the programs that are outside of this yellow circle, but are inside this like right side of this Venn diagram, is all the programs that are good but are rejected. What about this case? This is the type system that would be unsound and incomplete. It is incomplete because it rejects all programs in, like, it rejects lots of programs on the right side that are good, but it also accepts like this little part, this part of the intersection, that are bad, but they accept. So this is unsound and incomplete. That's bad. What about this type system? This type system would accept all programs that are good, so it is complete, but it is unsound because there are intersections between the yellow part and the left part of the Venn diagram. What about this? This is the optimal, right? So this type system, it will accept all programs that are both sound, or like it will precisely accept all programs that will never do X, and you'll precisely reject all programs that do X. So this is called sound and complete. This is the ultimate fancy goal that we try to get, but this is impossible if a type checker always terminates. And so let's first take a look at why, or like some examples of incompleteness that OCaml would reject, even though they would never, even though in runtime nothing is run. For example, people define this program called let f1 x equal to 4 divided by high. So 4 divided by high is definitely wrong, but if f1 is never called, this will not have any error in runtime. But OCaml just rejects that. So this program is incomplete, or like, sorry, this program is good, but incomplete. Sorry, I mean, this program is good, but OCaml will reject that. So OCaml's type checker is incomplete. Let's maybe take 30 seconds to read their code. Every single code is basically, or like every single function definition here is defining a division by high, but the division is never run. Any question, by the way? Right. So far, so good. Yeah. So why incompleteness? So almost any like error case X that you might think of that are checked statically, they're undecidable. So there's a mathematical theorem that says any static checker cannot do all three of them. They cannot first always terminate, second always sound, and be complete. So we're not going to jump too deep into that because this is not really about functional programming. This is more about the theoretical side of computing. If you're interested, feel free to take CSE 311 or 431. Yeah, 431 is a very fun class. I would 100% recommend. So have any of you heard of the whole team problem? Yeah, yeah. So the holding problem is is a problem of whether there exists a checker that the role of this checker is that it would check whether a program paired with an input would terminate or not. So I don't know if I have like space, but whatever. So imagine imagine a holding problem is solvable. So there actually exists such program that it can check whether another program that you want to test is terminated or not. This can solve a lot of tasks, which means that programmers would like just like programmers will not run into infinite loops anymore, because before executing their code, they can just like run the holding problem checker to check whether this program holds or not. Unfortunately, we don't have that powerful goal. It is proved to be doesn't exist, or this problem is undecidable. If people try to build this static checker that does all these three things, it is proved that this type checker can help solve the holding problem. But holding problem doesn't exist, or like doesn't exist a solution. So yeah, we just don't really have that powerful tool, unfortunately. Yeah. Now, we talk a lot about OCaml. Let's talk about a racket. What dynamic checking on the racket side does is that it just checks most things dynamically. What I mean is that almost no check, basically. So the dynamic checking is the definition, means that all the checks happen in the dynamic side. If the implementation can analyze the code to ensure that some checks are not needed, then we can just optimize them away. This is very convenient, very lenient for lots of cases that are not really strict. For example, the consoles can basically build anything. And anything except hashtag F is considered true. Yeah, very, very convenient. There is some misconception between what exactly is static and dynamic checking. For example, is the string foo plus the string bar allowed? Or is the string foo plus 3 allowed? Or what happens if we have an array access out of bound? This is surprisingly, this is not really about static versus dynamic checking. It is really about how the runtime semantics of the primitive is doing, which is it is really depending on how the program actually implements your plus. They are related because because this kind of checks is involved with the trade-off between whether you try to catch the bug sooner or later. Yeah. Now it's the time for us to argue whether static checking or dynamic checking is better. Yeah. So the view from the view from the audience is that we prefer OCaml over racket. Let's see if that's really the case. So claim 1, dynamic is more convenient. Why is that the case? Because dynamic typing, it lets you to do a lot of fancier and more powerful functionality instead of there are no too much restriction on a programmer, and programmers are always happy with that. For example, this function f would sometimes return a integer, and sometimes it returns a string on the racket side. And on the OCaml side, if the OCaml program tried to define such program, it has to first construct a type t. This type t variant type can either be an integer or a string. And you have to manually tag the type of y by integer or a string. This is a lot of work, basically. But we have another claim that says static is more convenient. This is because in static world, we can always assume that data has the expected type without expanding our code with more runtime checks or it will also prevent us from making lots of errors from the logical side. Yeah. In the racket side, where you define a function, cube, in order to make it sound, you have to check whether x is a number. because otherwise in runtime, the program might suddenly crash if you try to pass cube by something that is not a number. But in the OCaml side, you only need a single line code, let cube x, and this will handle all the tasks. Because in OCaml, it guarantees that the x that you pass in is an integer. You don't need more checks. Claim 2 is that static, actually, it prevents lots of useful programs. So in the racket code, in the racket code, this f of g, this would so this is an example of like of like a list in which elements have the different type. So we first define this function called f of g, which just like builds up, which calls g with 7 and calls g with true, and we have pair of pairs, which just like builds a list. I mean, builds a pair with 2 times of the argument. So if you run the racket code, it gives you a list in which the first element is a pair of 7, 7, and the second pair is true, true. This is definitely possible. But in OCaml world, this does not type check. You will never actually run it. It's very sad. So yeah, so static check. So in a static world, you don't have that many features. However, we may argue that static world, it will let you tag as needed. So yeah, so in a static world, when you try to expand your functionalities, the only thing that you need to do is just to define some variants. If you have a variant type, what you do is that you can always just add more variants as you code, which is very convenient. It is always possible to do more tagging, right? The claim 3 is that it's actually favoring static typing, that static will catch bugs earlier. So let's take a look at the racket code. This racket code is defining a power of x, and this power of x is like, within it has a lambda expression, so this power is queried. It might be hard for us to tell the bug here if we just read it. What's actually going on is that for this power x, that there needs to be a parentheses around power x, because power x itself is a function. Like, if it calls power x with another argument, this is violating the structure of power, because power only takes one single argument. So it's very hard to catch bugs in the racket world. But in OCaml, if you try to write a program that uses querying on the definition, but on the actual implementation, it is not using querying, this will not type check, and this will immediately tell the programmer that something's going wrong. But in the racket world, it will not tell you anything until you reach the point of power x minus y1. Claim 3b is that static only catches easy bugs. It will never catch all the bugs related to logic. So for example, in power x, instead of trying to pass in a multiplication, it passes a plus. This bug is not going to be checked by static typing. Yeah. So we are running a little bit out of time. There are lots of claims that basically covers every part that we can think of. We will post the slides, and if you're interested, there's a lot, very interesting. So yeah, there are basically arguments over any possible trade-offs that we can possibly find. So yeah. So our takeaway, which is better? This is a coarser question. So a better question would be, what should we enforce statically? There are lots of trade-offs that we've covered. So yeah, there's a lot to learn for both typing and yeah. So this is all that we have. Do you want to say something? Thank you for showing up.